Hello everybody, my name is Tan Çağatay Açar and today I'll be presenting to you my turn project which is image resampling using interpolation methods. The motivation of doing this project was it has a wide area of applications which is from medical imaging to satellite imagery to computer graphics, photo editing and machine learning. And actually the machine learning part is where why I wanted to start the project, because the company I was working for requested me to upscale images for their machine learning pipeline. So poor interpolation results in blurring, blockiness or ringing effects, uh, and this degrades the visual quality, and this affects downstream processing, which was crucial for my area. So I needed high quality interpolation, and we can achieve this high quality interpolation with bicubic or Lanczos interpolation, but these are computationally expensive, especially for large images or real-time systems, which in my case this was a real-time system. So the aim of this project was to implement an optimized image interpolation resampling with using CUDA on GPU platforms. We want to accelerate these algorithms as much as we can while preserving the output quality. So by doing that, we will enable scalable high performance image processing for both academic research and practical applications. So the official problem statement is we need to resample images with sampling frequencies fx and fy. These don't have to be same. These can be different, and these can be either lower than 1 or higher than 1. In my application, we are upscaling images, so it should be higher than 1, and these are normalized, meaning that if you select sampling frequencies that are equal to 1, you will get the same output image size, not necessarily the same image, because these methods can be non-preserving. So we will implement 4 sampling methods that are good for upscaling. The first one is the fastest one, which is the nearest neighbor, which when we want to sample a coordinate, we select the nearest pixel and directly copy its pixel values. Bilinear interpolation is a 2D linear interpolation in which when we sample a coordinate, we look at the 4 neighboring pixels and first do a linear interpolation in one direction for the 2 linear interpolations, and then we get 2 distinct values, and the other axis we do another linear interpolation, and that's how we do a 2D linear interpolation. And we have bicubic, which is slower but results in better output image quality. We do a cubic spline fitting. Now there are multiple cubic splines that you can fit, but specifically we are using Catmull-Ron splines, and to achieve it we use case kernel, which are getting into specifics, but to do this in 2 dimensions, this is the same idea. You do it in one axis, you consider 4 by 4 nearby pixels, so it was 2 by 2 in bilinear case. Now it's 4 by 4 in bicubic case. We do spline fitting in one direction, we get 4 values, then we do it in the other direction, and then we get our value for the coordinate that we are sampling. And the last is the slowest but results in the best, in my opinion, the best quality, which is Lanczos interpolation, which uses a windowed sync convolution kernel. Its graph can be seen like this. This can be used with different kernel sizes. You can select 1, 2, 3, 4. 2 and 3 are commonly used, but 4 results in better output image. And we will use 4 lobes. And when you lose 4 lobes, you are looking at neighboring 8 by 8 pixels. So this means we will have to sample 64 pixels when we want to sample an output pixel. Now, for prior work, these implementations, these interpolation algorithms are actually common in industry, and OpenCV is a very rich and well-known library for C++ and also has Python ports. And it has CPU implementations of all mentioned algorithms. It also has contributed packages, and these have CUDA implementations except for the long source interpolation, so we cannot test this. There is also multi-threading support for CPU implementations, but I disabled it to compare it, be able to compare it with serial code performance. But all other optimizations are enabled, such as compiler optimizations and fast math optimizations. So the algorithms are also implemented by me. I implemented custom CPU serial codes in two flavors. One is we access by byte fashion. Since we only have 3 channels RGB, it's not 32-bit aligned, so I didn't touch it in the first version. Then I converted to 4 channels. I added essentially an alpha channel, which is ignored, and I tested with that to see if 32-bit aligned access speeds up things. And for GPU kernels, I implemented several approaches. So first I launched threads per output sample, and I wrote the kernels for that, which was simpler to write because all the calculations are done once and I load pixels as needed, but this results in redundant memory access because since we are sampling usually for upscaling, we are sampling more in between input pixels. We are each thread, sometimes some threads read the same input pixels, so same memory locations, but these are redundant. I tried to fix it with make it lower with reduce this negative effect with shared memory, which helped a bit, but then I used a different approach, which was to launch threads with per input pixel, which loads a nearby 8x8 pixel per thread, and then calculates to corresponding output samples. So this way, each thread would load once from memory, but do several output sample calculations, which was better. And then CUDA provides texture objects that give some benefits in 2D like data structures, which image is. So I use texture objects with same approaches and solve their improvement. So here you can see the texture object configurations for each algorithm. I used there is a bilinear interpolation support in hardware, which I used it, which was not applicable for threads per input pixel approach, because you just use the hardware interpolation per output sample, and there was no other way without using it per input pixel. So I use two different input images with very different input sizes, and I upscaled the image by 2 and 4 for testing purposes, and for all run configurations I tested them 10 times, and I averaged their results. And you can see for CPU code, the OpenCV's implementation, except for nearest neighbor, beats my custom code in every algorithm for all run configurations. I think for nearest neighbor, since I don't use the CV mat object, there is some overhead while using that. But for bilinear, bicubic, and Langsos, I think there is some sort of optimization that I'm not using, like lookup tables, because Langsos and bicubic include cubic or sync calculations, sinusoidal calculations that slow down the process. But for calculating with for comparing with GPU kernels, I use the best performing codes for each algorithm for fair serial code comparison. For when we look at GPU kernels CUDA implementations, OpenCV's implementation, we see that it's slower in any case compared to my custom kernels, which was not expected. I expected, because this is an open source with community developing it, it would be, I would expect it to be faster, but I think there is some overhead that they cannot get away. So when I compare the different approaches I used, I can see directly that using texture object improves the performance of the codes, except for thread per input for some cases of nearest neighbor. I believe this is the case because we are just moving data around in nearest neighbor, and when this is the case, texture objects cannot show themselves, but when doing other calculations and loading more than one pixel per thread, texture objects spatial caching, two-dimensional spatial caching, shows its difference. Also, when aligning pixels, aligning memory to 32-bit memory addressable space, we see a huge jump in speed up, huge performance improvement. And also thread per input calculations are much faster generally, in one exception being bilinear, because you can see that when using texture object this is not applicable because we are using hardware support here, and the optimal and best implementation is when we use thread per input and texture when we use texture objects, again with the exception of bilinear, because we cannot do it, and with using hardware accelerated code, it's the best for that bilinear. So the results are actually when you see output images are identical for all implementations of code. So we are preserving output quality, and when we compare, we can see that Langsos also preserves the contrast as well as smoothness, while it is more prone to ringing, but bicubic is less prone to ringing, but the contrasts are a little bit degraded. We see a 99.26% speed up from the fastest CPU implementation when it's compared with the best GPU kernel. Using texture memory speeds up the kernels, but this speed up varies from 3% to close to 53%. This change depends on the kernel's global memory usage. So the heavily a kernel depends, it will its speed up will be more dependent on using the texture memory. So the best approach, as I said, was to launch kernels threads per input pixels using texture objects, except for bilinear interpolation. So custom CPU code was slower than OpenCV's, and many optimization techniques might be missing from our code, like lookup tables. But since I didn't use these, I also didn't use these in GPU kernels. But we were faster than OpenCV's CUDA implementation. There may be still potential performance gain in GPU kernels that we didn't explore. But this doesn't matter for the aim of the project, which was to explore memory and thread management techniques for optimizing these interpolation algorithms, which was the scope of this course. Thank you for listening. Now we will show a quick demo of our project. Okay. So if there is already compiled code here, and if I run the CPU code for the second sample, let's run it for the first sample image because it's I ran it for second accidentally. It takes some time, and now we can see the output image here, and the first image was 5484 to 3926. We should double the output image, and you can see from here, bottom left corner, it's 10,968 to 7,852. And if we zoom, we can see that the image is upscaled. And let's compare it with the we can see that it is upscaled and the details are enhanced. Now let's try the GPU code. This took 9 seconds to execute. Now for the same run configuration, it took 75 milliseconds, and this is not our fastest long-source interpolation kernel. It should be the version 4.1, and you can see it took 28 milliseconds. And if we now take a look at the output image, you can see the image size is the same. It is resized by 2, and if I again zoom, it is identical to the output of the CPU one. And if I run the texture code like that, and the fastest should be V3, it took 26.2 milliseconds. And if I take a look at the output image, the image's output is the same. Let's zoom, and we can see the output details are enhanced. Now let's try changing one of the sampling frequencies. Let's change the one in the X direction to 3 to make it a little bit different than the shown output configurations. It has, now you can see the output image dimensions are different, and if I can zoom, it's a bit hard on my GPU, I believe. Let's reopen it. You can see that the image is a bit stretched in the X direction, and if I do it ridiculously high in the X direction, you can see that it's very much stretched now. And we can do this in the other direction as well. Or we can make this smaller. And this would result in less. But long source is not great for image downscaling. Area interpolation is better, but this is not included in the project. Thank you for listening and watching. Have a nice day.